Welcome. In this video, we are going to talk about what multi-step reaction energy profiles look like and what a catalyst does to our energy diagram and how they help speed up reactions. And if you're looking in our textbook, if you have a hard copy of the book, all of our kinetics is in chapter 13. If you're looking at the e-text version of it, it's been updated. I believe it's in chapter 14. So you can look there for reference on kinetics. So a multi-step reaction, let's look at what this energy profile would look like. So in previous notes, we talked about these energy diagrams, and on these diagrams, the y-axis is energy, the x-axis is the reaction progress, sometimes refers to as a reaction coordinate, and we go from reactants to products, and these graphs always go up first and then down. And the amount that they go up by, we call that the activation energy. That's the energy input needed to get that reaction started. So this would be what a single step reaction would look like. We know from experience now that a lot of these reactions actually occur in these multi-step mechanisms. So a reaction might take place in a series of 2 steps or 3 steps or 4 steps. And this is what a reaction profile would look like for a 2-step mechanism. So this one right here would be step 1, and then this one over here would be step 2. So if we've got 2 steps, there's going to be 2 bumps. If there's 3 steps, there's going to be 3 bumps. You get the idea. And just a reminder kind of vocabulary here and what these various parts represent. The peaks here represent what we call the transition state. Sometimes they're referred to as the activated complex. It's some in-between unstable thing where some bonds are starting to form and some bonds are breaking. This right here, this dip in between, this is where we might see our intermediate in a reaction. So let's look at another side by side here. On the left, we've got a single step reaction with no intermediate. So imagine this scenario, it's a really straightforward, simple reaction where A and B or reactants collide and they form C. And that's it. So just one step here. This area is our activation energy. Then the difference between the reactants and the products, this is our change in energy. We refer to this as the delta H of your reaction. That's this area. And then this right here, activation energy, we sometimes use the symbol E sub A for activation energy. Over here on the right, we've got a 2-step mechanism. So our overall reaction is, our reactants are A and B, and our product is C. And so that part kind of looks the same here. But this reaction actually occurs in a series of 2 steps. So first, one molecule of A and one molecule of B collide to form AB, which is the intermediate. And then AB collides with another molecule of B to form the product C. So if we look at this one, so we first have this first step here where we form the intermediate. So this is where AB exists, is right here in this dip between the peaks. And then your intermediate AB collides with another reactant to form the product C. So as we got a 2-step mechanism, so we've got 2 bumps on our reaction diagram. And if you remember from, again, previous notes, we said there's a relationship between activation energy and rate. And that relationship is an inverse relationship. So the higher the activation energy, the slower the rate, or the lower the activation energy, the faster the rate will be when we're comparing like 2 things at the same temperature. Okay, so we can use this to analyze a curve like this and figure out which step in this mechanism, is the rate limiting step. So if we take a look at this mechanism here, we've got 2 steps here. Here is the activation energy for step 1. And over here is the activation energy for step 2. So what I'm going to notice is the activation energy for step 2 is a lot smaller than step 1. And remember, things with a smaller activation energy are going to be faster. So therefore, this one with the larger activation energy, this one must be slower. So that means that step 1 is the slow step in this reaction. So Let's actually go back and look at this previous slide as well. If we go back and look at this one, same kind of idea here. Notice how the first step has a higher activation energy. So it is going to be the slower step. This one over here has a lower activation energy, so it's going to be faster. So I could actually now go back to my reaction mechanism and say it looks like step 1 is my slow step, step 2 is my fast step, and then I can write my rate law because I know the molecules in my slow step. So my rate law involves 1 molecule of A and 1 molecule of B. So it's first order in A and first order in B. So we can see how these energy diagrams connect to these mechanisms here and can help us figure out the rate law. Here's what it would look like if the second step is the slow step. So, and just one thing I want to point out is make sure when you're thinking about these activation energies, you want to measure them kind of from the starting point. So here's this, activation energy for step 1. Here is the activation energy for step 2. Notice how step 2 has a much larger activation energy, so it's going to have a slower step. Oh, if you're wondering what this means, RDS, some people use that shorthand for rate determining step. So it's the slow step in the mechanism. And let's think back to what we talked about earlier with this whole collision theory and the idea of this activation energy being like a barrier that your reactants have to get over in order to react and form products. So in order for a reaction to occur, you need to have a collision, and that collision needs to occur with enough energy, and that energy of the collision needs to be greater than the activation energy barrier. So in order to speed up a reaction, we want to increase the likelihood that the collision energies will be greater than the activation energy. So there's kind of 2 different ways to go about this with speeding up a reaction. One is you can increase the temperature. So if you increase the temperature, you are going to increase the kinetic energy of the particles that are moving around. And if the individual particles have a greater kinetic energy, they will also collide with more energy. So that will increase the collision energy. It will also increase the number of collisions too, since they are moving around, more often. So increasing the temperature actually does 2 things. It's going to cause your particles to bump into each other more often, but then very importantly, it's going to increase the energy of those collisions that happen as well. So you're going to have more collisions, and a greater percentage of those collisions will have enough energy to result in an actual reaction. Another thing you can do to make a reaction go faster is if we could somehow decrease that energy barrier. And it turns out this is what catalysts do. So catalysts will actually lower the activation energy, and that can make the reaction go faster. So again, looking at side by side here, if you want to speed up a reaction, one way in which you can do it is by increasing the temperature. So if you increase the temperature of a sample, then you're going to have a greater fraction of your particles will have sufficient energy to react. So here's in our lower temperature sample, only this very tiny small fraction of my sample had enough energy to react. When I increase the temperature, now I have a much greater percentage of my sample is going to have sufficient energy to react. So in my green sample, more collisions will result in a reaction. So my green sample, the reaction is going to go faster. Okay, so that's what's happening with temperature. Now let's look at catalysts. So what catalysts do is catalysts will act to lower the activation energy. So they'll actually change the reaction pathway. So here's an example here. The blue one shows the regular reaction, no catalyst. Pink one shows the catalyzed version. And some things to keep in mind is that the reactants and products don't change. And the overall delta H or delta E for the reaction stays the same. Okay. The only thing that changes is the height of this peak in the middle. So the transition state changes, which changes the activation energy. And when we lower the activation energy, that's going to make the reaction faster. The reason why is if we lower the activation energy, more of those collisions are likely to have enough energy to react because you have just lowered the barrier. So now a greater number of your collisions are going to be able to make it over that barrier. Here's another example showing what a catalyst looks like. The red one would be an uncatalyzed reaction. The blue one would be a catalyzed reaction. And let's think about how the catalyst and activation energy would relate to those Maxwell-Boltzmann curves. Remember, Maxwell-Boltzmann curves are things that we also first saw when we talked about kinetic energy of gases, and we talked about kinetic molecular theory. And whenever you're looking at a graph, you want to pay careful attention to what your axes are. So what this graph is showing us is the number of molecules at various energies. So it's basically showing us like the energy distribution of a sample. And this is a sample at a certain temperature. Let's just make up a temperature and say it's 50 degrees Celsius. Okay. And you have a reaction that has a certain activation energy. And so notice that at 50 degrees here, this original reaction, only a very small percentage of my sample actually has enough energy to react. I'm going to put a number here. I don't know what it is exactly, but let's say call this like 5%. So of my whole sample, maybe only 5% of my particles actually have enough energy to make it over this energy barrier and actually react. If we add a catalyst to our sample, what that does, it lowers the activation energy barrier. So it makes this line shift over here to the left. And so now this whole pink and gray area shows how much energy, shows what percentage of your sample has enough energy to react now. And maybe that's, I'm going to just make a estimate here. Let's say maybe that's like 20%. So what happened is the temperature is still the same. It's still a 50 degree Celsius sample. So the energy of the individual particles stayed the same, but we lowered that activation energy barrier. So as a result, now a much greater portion of our sample has enough energy to make it over that barrier. So that's really key. Without changing the temperature, now we have a greater number of particles that have enough energy to react. So the reaction is going to occur faster. Because if 20% of your collisions result in a reaction, that's going to go a lot faster than if only 5% of your collisions resulted in a reaction. There's a demo of elephant toothpaste, which you can find some great videos of this. It's a great demo. I don't want to take a video of a video because I think that won't turn out very well, but there's some great videos you can look at with elephant toothpaste. And what elephant toothpaste is it's the catalytic decomposition of hydrogen peroxide. I'm actually going to go and show this slide first. So here's the overall reaction. So hydrogen peroxide will naturally decompose on its own. This is something that occurs spontaneously, but normally it happens really slowly. So if you were looking at a sample of hydrogen peroxide, it would look like nothing is happening. If the reaction is occurring so slowly, you don't even see it happen. But if you add a catalyst, and there's a variety of catalysts you can use. You can actually use a biological catalyst. You can do this with yeast, or you can do it with like sodium iodide or sodium bromide. And when you add a catalyst, it will change the reaction pathway and make this reaction go a lot faster. It's still the same reaction. You're still turning hydrogen peroxide into water and oxygen gas. You're just getting there by a different route, and so it's occurring a lot faster. So if you look at this visual, shows the uncatalyzed reaction is in pink. So you can see this is your original activation energy. It looks relatively high. And then if your catalyzed version, you see how it's a two-step mechanism, but each of these steps has a much lower activation energy than my original. So this process is going to occur a lot faster than my original uncatalyzed reaction. And here's what these two steps look like if you're curious. So if we add these two steps up, we'll see that iodine cancels out. And so that's actually something we will notice with a catalyst, is catalysts are kind of like intermediates in that they cancel out and they don't show up in your overall reaction. But what's different about a catalyst is it will be a reactant in an early step, and then a product in a later step. Sorry, my handwriting's messy. In a later step. So notice how iodine, we put iodine in initially in the first step, and then the iodine gets regenerated here in that last step. So the iodine is not technically a reactant because it doesn't really get used up because it gets popped out here again at the end. So we call it a catalyst. And this reaction also has an example of an intermediate in it. So the intermediate in this case would be the OI minus ion. And an intermediate gets canceled out of the reaction, but it gets, the difference with an intermediate is an intermediate is something that is formed in an early step and then used up in a subsequent step. Your catalyst is added in an early step and then like regenerated at the end there. So that's your example of a catalyst versus an intermediate. And then if we go and we add these up, we'll notice that on the left we have two hydrogen peroxides. And then over here on the right, we've got two molecules of water, and then we've got one oxygen. So these two steps add up to this overall reaction. It's just this catalyzed pathway occurs a lot faster than this kind of original mechanism on its own. Okay. And so we add up the elementary steps to get the overall reaction. We're going to identify who the catalyst is. The catalyst is iodine. OI minus is the intermediate. And then let's assume that the first step is the slow step, and let's write the rate law here. So if the first step in this mechanism is the slow step, then the rate law for this catalyzed reaction would be K H2O2 times iodine. And you might say to yourself, wait, that's weird. Iodine shouldn't be part of the rate law because iodine is not a reactant in the overall reaction. But it makes sense that a catalyst would be part of the rate law, right? Because if you add more catalysts, it probably will go a little bit faster. So it's actually okay for catalysts to be part of the rate law. So if you're thinking about what can be included in the rate law, reactants can be included in the rate law, for sure. And catalysts can also be part of the rate law, because it makes sense if you add more catalysts, it's going to go faster. Something that should not be part of the rate law is an intermediate. So intermediate should not be included in the rate law, but reactants, whoops, and catalysts can be. And then let me just go over a couple examples of catalysts. So enzymes are an example of a biological catalyst. Enzymes are super important, doing all sorts of things in your body constantly. They're going to keep our reactions in our body happening at a reasonable rate to keep us alive. Okay. And enzymes are these big proteins that have specific shapes that allow them to combine with certain reactants. We call those the reactants the substrate when we're talking about enzymes. So enzymes are an example of a biological catalyst, and this is something you might talk about maybe in a biology class. Enzymes are large proteins made up of amino acids. An example of an enzyme that you may have heard of before is lactase. That's an enzyme that allows your body to break down the sugar found in milk, lactose. Some people have a different version of lactase that does not allow them to break down that lactose very well, and then that is what results in people being lactose intolerant. So that's an example of an enzyme there. And here's another example of an enzyme. And enzymes are just like other catalysts where they can change the reaction pathway. So here's an example of an enzyme that's taking a one-step process and turning it into a three-step process, and that's going to speed that process up. Another interesting catalyst to think about is a surface catalyst. These are called heterogeneous catalysts. That's when you have where the catalyst itself is in a different state of matter than the reactants. Metals are common examples of this. So platinum is often used as a catalyst. And here's an example showing this. So this down here would be the metal catalyst, and this would be like a hot gas being swept over the surface, and this right here is going to catalyze this reaction. An example of this heterogeneous kind of surface catalyst that you might see is in your car. So a catalytic converter in cars, it's made of metal. So the converter itself, the catalyst itself is this metal, and the hot gas, these exhaust fumes from your car, are going to pass over this metal, and this helps speed up the combustion reaction. So it'll help oxidize some carbon monoxide and your non-combusted hydrocarbons to form CO2 and H2O, and it'll reduce some nitrogen oxides and turn them into nitrogen gas. So this is something that will speed up this reaction and make your exhaust coming out of your car cleaner. All right, so again, a review here. Increasing the temperature will increase the reaction rate because if you increase the temperature, you will now have a greater portion of your sample will have sufficient energy to react. Increasing temperature will also increase the number of collisions. And that's also what increasing concentration does. If you increase concentration, it will increase the number of collisions. So that was something that will also help your reaction go faster. And with catalysts, the way that catalysts speed up a reaction is they lower the activation energy, and that will increase the reaction rate because now more particles will have sufficient energy to make it past the activation energy barrier because you have lowered that barrier. So now a greater fraction of your sample has enough energy to react. All right, and that's it. Thanks for watching.